So today we're going to do the last of my sort of three-part introduction to geometric perception. I decided to make it 3 lectures. Actually, the original syllabus had only 2, but it's been an opportunity for me to introduce some of the optimization ideas that we're going to use more too. So I hope you're okay with doing one more day of this. I think it's really, really good. And I think I hope that it's sort of clear. I'm actually going to jump right into the whiteboard here. But I hope that the organization of the 3 lectures is fairly clear. I'll try to remind you what's happening here. It's unable to connect, it says. Oh, that sucks. I also updated my browser, and now Zoom is not connecting. I need a few seconds to debug this. Let's see. Don't have any ports for that. That's a bummer. Everybody says, Zoom, update your client. It'll be great. There's new features for breakout rooms.
If there's one thing I learned from using Linux is don't update. This isn't Linux, but still.
I think I have a fine workaround, but good. The only caveat is that I'm now on battery power on my computer and the fans are already spinning. So if I disappear halfway through, we'll see how it goes. Okay, good. Sorry about that. All right, we had 3 lectures on geometric perception to start us off. Hope that's all coming through good. Okay, so day 1 was sort of our clean point clouds. And we did the basic point cloud registration algorithm. The main focus was registration, and ICP was our main algorithm, right? On day 2, we went to messy point clouds. And I think one of the takeaways I hope you got was that actually for Gaussian noise, for sort of simple additive noise, the ICP approaches that were based on least squares was actually already robust. I mean, not super robust, but like it's actually doing sort of the right thing by having a least squares objective in the middle. But for outliers and dropouts and other things like that, the outliers in particular caused a big problem. We needed to generalize our notion of correspondences. And I gave a few ideas along that in that direction. We talked about ransack, which I'll do on your problem set. We talked about this pairwise distance as being a way to vet obvious outliers. And then we talked about the coherent point drift algorithm, which was the soft constraints. The CPD was the way where we just put Gaussian weights on top of all of our pairwise distances. And we did basically a correspondence between every possible pair of points. And the the big theme there was basically reject things that are too far. Basically we wanted to try to somehow, the problem was that points that were far away, these outliers, would get a large distance. If they were added into the cost just like every other distance, then they would dominate the cost and totally mess up our optimization. So we somehow had to mitigate the effect of these very far away points. So we're removing them completely as one way. The CPD way was to weight them very small, right? So that the cost that they incur is somehow truncated. And then today, what we want to do, we're going to add all the additional constraints that we've been leaving out. So in particular, there's two big constraints that we're going to talk about: the non-penetration constraints and the free space constraints. And you'll know what those are by the end of the lecture if you don't already. I mean, the non-penetration is sort of easy and obvious, and it hits you right in the mouth right when you start trying to use this stuff, because the first thing that happens is you get your beautiful simple system. You've got a table. You put your box on the table, and you get your scene points that come in with your perfect depth camera. They taken from here, for instance. You get all these views, and there's nothing more frustrating than to watch your ICP algorithm go, here's your fit, and it's like halfway into the table. Or even worse, it could be, sometimes it's actually worse than that. And boy, the people who are smiling are the ones who've seen this. This happens for real, and it's just, how can't I just tell you not to do that? Don't stick. For their table, maybe what people would typically do is just only look for positions and rotations and just make it a planar problem. But that's obviously a pretty limiting road, and there should be a better solution. Okay, so there's nothing more frustrating than that. So let's spend a little time figuring out how do we resolve it. How can we avoid it? Given, as our starting point, we were writing objective functions at the end of last time, which was minimizing, for instance, R in, remember I used my notation, for R it's just SO3. Meaning R is some valid rotation matrix. And I was writing the sum over all possible pairs weighted by some weights that were, in the CPD case, were given by these Gaussian kernels, but just somehow some decaying function. And this is the rotation only case because remember we showed that we can actually separate those two out, right? And we had separated them out by putting it in the relative coordinates, and then this is actually mj si minus p s bar squared, for instance. Okay, so what do we do to that optimization to start stop it from putting things into the table? Well, the obvious thing is you want to add constraints, just like we did for the Jacobian-based control. We said it's one thing to write the Jacobian and rely on the least squares solution. It's another thing entirely to get a robust solution that has obeyed the constraints. So what kind of constraints would we want to add for something like this? Well, we had model points as well as scene points, right? So in this solution that we don't like, I've got a whole bunch of colors at my disposal here. In this solution that we don't like, the rotation matrix, the transform in its totality, somehow put the model points into a place that we don't like. So you could imagine writing a constraint directly on the model points. just make sure the chat is visible in case anybody says anything. Okay. So what does that look like if you're, I'll just write it with the whole pose because we can do that in general, but let's say maybe you'd like to say for all of your model points projected in, you know, whatever X I'm solving for, you know, that better be, well, I'm going to write it as a general linear constraint. But for instance, you might say that you'd like my world projection of all my model points to be like greater than 0. That is just a version, a particular version of this where I've chosen B and some coefficient on X. So what's wrong with, or, I mean, that is the right answer in some sense, but why does it require more work? Because so far we've been relying on the special structure of that quadratic form subject to exactly the constraints of the rotation matrix. And that had a special solution that was based on the SVD. But if we start adding more stuff in there, then the SVD doesn't give us a nice solution, right? So we have to somehow, you know, have a more general solution technique. The same way, it's exactly the same as the way that in the Jacobian-based controller, we had the pseudo-inverse as our solution, but once we start adding constraints, the pseudo-inverse wasn't the solution by itself. And here it's the same thing as that the SVD, which is really like the pseudo-inverse here. It doesn't give us the solution, so we're going to have to go from our closed form solution, you know, by calling SVD, to a numerical solution based on optimization. So now, most optimization solvers, if you give them the constraint that R is SO3, they will, I mean, I guess they don't laugh at you, but they sort of like, they won't accept it, right? So there's not an interface even to say, please make R be a rotation matrix. The types of ways we've been writing it before, you know, R transpose R equals the identity and the determinant of R equals +1. Those are difficult constraints to add to an optimization problem to hand to a solver. This is, we said, in a quadratic equality constraint, right? Which is a non-convex constraint. Because if I think of all those points on the unit circle, like in the illustration, right? So I have a solution that puts my rotation matrix coefficients here. There's another solution that would be valid here, but the straight line between them is not a valid solution. So it's not a convex optimization. And this one similarly, the second one is also not a convex constraint. So this is where we have to start doing the relaxations in order to hand them to our solver. So we're going to relax the constraint to, in this picture, it's going to be to the unit disk. So I'm going to say, let's pretend all of those values are viable. And now suddenly my optimization is over a convex set. And more generally, I'm going to say R is in, there's a couple different notations you could use. I think, without being precise about it, I'm sorry, but I'm going to say it's in somehow the convex hull of SO3. Okay, that is sort of, I think that is can be made rigorous. I think it conveys what I want right here. And I should say that this idea of relaxation, you know, I've mentioned it a few times, but it is very common in optimization. A standard way, if you have a problem that is sort of too hard because of some constraint, it's a principled approach would be to find a softer constraint that allows more solutions. And then when things are going really well, actually, you can sometimes still prove optimality. If, for instance, the solution to my relaxed problem happens to satisfy my constraint, then life is good. So if, for instance, I solve some optimization problem, and if I had my my quadratic bowl, for instance, remember the graphic I had in GeoAlgebra, whatever it's called? If that pulled me to the edge of the unit disk, then it actually does satisfy the unit circle constraint, and I've got an optimal solution. So let's think about what it looks like first in just the 2D case where I drew those pictures before, and I think it's easy to think about. So remember, the trick in 2D that made it really nice is that I can parameterize the 2D matrices as A, B, negative B, A. So that's good. The R transpose R equals identity and determinant R equals +1 both give me the same constraint. They give me A squared plus B squared equals 1. That's the hard constraint. So I'm going to relax that to A squared plus B squared is less than or equal to 1. That's the difference between the unit circle and the unit disk. Okay. So now we can write our pose estimation. Is whatever sum we like, Cij, for instance. All of my favorite stuff here. Subject to A squared plus B squared less than or equal to 1. And I can start saying things like, this gives me the ability to add things like R times my PMJO is greater than or equal to 0, for instance. That's an optimization problem I can hand to a solver, and the solver will do good things with. It turns out you've used mathematical program in Drake a little bit. Rather than tempt the fate and go back and forth and show you the code, let me just stay on the iPad for a minute here. But so mathematical program, I mean, it'll look something like this. I can actually make new decision variables, A, B, new continuous variables. And I can make my rotation matrix by setting those up. I can add my cost the same way you did. This time with my data matrices, right? Because I have this objective here. I just have to add that in with add cost. And there's a particular way which it's a for what looks like a fairly benign constraint, there's a sort of a tricky way to add that into the solver. It's with a Lorenz cone constraint. I will ship the example with the notes tonight, but that basically imposes this constraint here. And it's interesting. So this is a class of constraints that are called the second order cone constraints. And it's a class of optimization problems that are called SOCP. Now, again, it stays in the class of convex optimization, so you can expect your solver to do pretty well as long as you have a solver that supports it. Now, I have a sort of a funny idea about how much optimization I should cover in these lectures, because I hope it's okay. I've chosen to sort of occasionally drop some of the more advanced things. I know some people know them well, some people haven't seen optimization. I'm not like expecting you to suddenly be masters of SOCPs because I wrote them once on the slide. But I hope it gives you a sort of a place to read more if you're interested, and there'll be links in the notes. But I think it's sufficient for to be a user of this, for instance, to just appreciate the way that it gets added in. Maybe you could also appreciate that actually the mathematical program interface in Drake is doing a lot of work behind the scenes when you add the constraints. If you add only quadratic objectives and linear constraints, it calls a special purpose solvers that's really good at quadratic programs. If you add a nonlinear objective or a nonlinear constraint, it'll call a nonlinear programming solver. If you call one that has second order cone constraints, it calls a different solver that's appropriate for second order cones. And we can't say, I mean, we have a variety of solvers that are available. Not all of them are free, so I can't. So some of them require licenses and stuff like that. But it's actually a pretty sophisticated front end on how to write optimization problems. Okay, so but the important point is you can write an optimization problem that will consume constraints of that form, and it's still an optimization problem that you would expect, like in our Jacobian, to give a good solution if it exists, or say explicitly that it doesn't exist if for some reason you hand it something intractable. Okay, so how well does it do? Again, the example might be a little better, but I think even with on the whiteboard, we can sort of have an idea of how well it does. And it's really exactly the picture that that we drew before in that interactive animation I made, where the constraint was here, the objective function was trying to push us to a solution that actually, in the no noise case, the minimum of the quadratic form was actually, on the circle. But we've added something different here. We've said that there's some linear constraints on these parameters. It could say, for instance, that if you were to go over here, you would be in the table, so you're not allowed to go here. So what can happen, right? I mean, if the optimal solution based on the data was trying to push me over here into the constraint, then it's going to do its best and come back to someplace like this, right? We've given it the freedom to come inside the circle, but it's not allowed to go outside the circle, right? So it might come up with a solution like this. When you're away from the constraint, you'd expect it to give the same performance that you got before, right? How well does it handle noise? Well, noise is going to, basically the data is going to lie a little bit about what's the right solution because of that data, that noise, but it'll move it in a sort of benign way, hopefully staying in the vicinity of the solution if the least squares objective is good. So if it ends up a little bit outside the circle, then the solution it'll come back is going to give back is the one that's on the circle. If the noise gives me data points that would be a little inside the circle, then it's going to return a point here, which is not a valid rotation matrix. It's but it can be fixed to be a valid one if you like, or you can keep the solution that is telling you what describes the data best. Okay. So what's a case where if my noise happened to, for instance, if I had a box on the table with noise that just happened to be sort of, on the interior of the box, for instance, then a rotation matrix here that has column vectors that are in magnitude less than 1 is effectively shrinking my model points as well at the same time as it's trying to fit the data. So you could come up with a solution that it's basically saying, yes, I can fit the data best by not only rotating my box, but also shrinking a little bit. That's what the solutions are on the interior. If my noise happened to pull me on the outside, that constraint will be tight, and it'll be sitting on the right solution, hopefully. So I would say in many ways, this is still a solution that is robust to additive Gaussian noise. And the question becomes again, how well does it do on outliers? The way I've written it here, we can use the CPD kind of ideas to set those gains small for the outliers. So that's potentially okay. It can combine a lot of our best solutions. Questions on that?
Russ, could you speak to the class of geometries you can represent collisions for this? Is it like, are we considering half planes only?
Good. In fact, that's the next thing I was going to say. So you can't add arbitrary non-penetration constraints like this, right? So Terry's exactly right. So this worked because I'm saying the model points are not below some infinite half plane constraint. So it's that linear constraint is really saying that there is no place over here that I can go. If I have multiple objects in the scene, for instance, I could try to fit two objects at the same time if I wanted to, or I could just have another object that I know exactly where it is, and I want to avoid that. But it's not an infinite table. It's a finite object. This is no longer a convex constraint, and so it doesn't fit in my simple this simple worldview of linear constraints. In fact, so why is that not a convex constraint? Because I could have a solution that satisfies it with my box over here. I could have another solution with my box over here, but there's a solution directly in between it that doesn't satisfy those constraints. Okay, that is also true in rotations, which is what I should have done a rotational example. So since we wrote the rotation only version of it, but you can imagine a box you're happy with here, a box you're happy with here, but the box that's rotated in between it is not a valid constraint. Okay, so in general, non-penetration constraints you would think of as being non-convex constraints. Also, I should say the tightness that we're talking about here is partly due to the fact that we had a clever parameterization in 2D. In 3D, the convex parameterizations of the rotation matrices is more subtle. It requires, I wasn't going to do it here. I'll give a reference to it, but the convex hull of SO3 requires the best relaxations, the tightest relaxations, requires a Schur complement and some semi-definite programming, semi-definite matrix constraints. There was some good work by James Saunderson that I will link in the notes. Complement. Semi-definite programming. Okay, I want to stop for a second and let you make sure you're following. So here's a little check yourself, kind of make sure you're following it here. I guess mine says resume, yeah, but yours will probably say start, I think. So here's a couple questions. I'll take a little breather, charge my laptop for 30 seconds, and then or 2 minutes, and we'll come back. All right. Hopefully that was useful to just take a second and think it through. I'm not sure exactly what the right amount of time is, but not maybe enough to get a sandwich. Someone said they got a sandwich last time, and that was really useful. Maybe not enough time to make a sandwich, but hopefully enough time to just think about if the message is coming through. Okay, so Terry already asked, how far do we get with these convex constraints? And the answer is we don't get everywhere we want to be. This is a real problem, not just, we'll see a couple different instances of it. It's not only when you have multiple objects in cluttered scenes. There are other cases where you'd like to be able to handle more general constraints like that. So at some point, as much as I like the convex optimization approach, and I think it sheds light on the geometry of the optimization problem as well as the geometry of the physical problem, at some point we're fighting a losing battle, right? And it's time to just say we're going to solve a nonlinear optimization problem, a non-convex optimization problem. Okay, so in fact, Anubhav was asking that earlier in one of the other lectures. You were asking if you could do it in Euler angles, and this is a case where you can do things in Euler angles if you're willing to solve the nonlinear optimization. So let's understand. Go back to slightly less colorful. So nonlinear optimization is a form of non-convex optimization. It can handle functions that are obviously nonlinear. It still tends to, it refers to a class of solvers that still likes functions that tend to be smooth, for instance. So our objective functions before were nice convex functions. For a nonlinear optimization problem, we can handle more complicated landscapes that need not be convex. But the contract you get from a nonlinear optimization solver is weaker. It says, I'm going to just do my best effort, and I might return this solution. I might return this solution. I can't promise. And the real frustrating thing is you don't even know whether the solution it found is the best solution or not. There's sort of no way to know. Okay, so it'll return some solution that should be a local minima, or it could complain saying that I had some numerical issues. And those are real if you start having strange functions. If you start asking it to optimize strange functions that kind of have discontinuities or whatever, your solver will say, something's fishy here, I can't do it. But for the class of smooth objective functions, acceptability of local minima, which is what we're going to now, and even non-convex constraints, but again, ideally smooth constraints, so, governed by smooth equations. This is a bigger class of optimization problems with weaker guarantees. Okay, so we can write, we could actually just hand our nonlinear optimization problem. This is a valid nonlinear optimization problem. We could actually write our full optimization. I'm going to not write it yet again, but you know what I would write. I could hand it those constraints. Those are non-convex, nonlinear equality constraints. And it will do its level best to try to satisfy those constraints. Now, in practice, there's a number of different solution techniques that people use for nonlinear optimization. The one that we default to in Drake and for this class, which works well in these kind of problems, is it's a sequential quadratic programming solver. Or SQP, which just by the name, you can sort of guess that the way it tries to solve these more complicated problems is by making local quadratic approximations of the objective function and local linear approximations of the constraints. Solve that problem, find your new solution to take your approximation around, and repeat. So that can have fast convergence but it can also still get stuck in local minima. And it can handle constraints that look like this, but that's not the ones that are going to make it happy. It's going to try to approximate those as linear equality constraints along the unit circle, right? And it will do its level best and it will converge, but you're not doing it any favors by giving it one of its good problems. But here, so a lot of our work here and our choice even of choosing the rotation matrices as our parameterization, like the coefficients of the rotation matrices as our decision variables, that was mostly to keep our objective quadratic and our constraints linear, okay? If we've given up on convex solutions, then we can also go to the maybe more natural or certainly the unconstrained version of the problem. So in 2D, I could write the same, maybe even a better optimization for my solver by say minimize over theta, okay? Sum over ij, cij, and then instead of using r, I'll go ahead and write my objective function with the rotation matrix written in terms of theta times all my model stuff. And then we actually don't need any constraints, right? Because every valid theta, any real valued theta is already restricted to be a valid rotation matrix. This is now a nonlinear objective function, but it's compatible with the solvers and is actually probably nicer than trying to ask the SQP method to do some sort of local linear approximation of that ugly thing. Okay, so this is a more complex objective. But unconstrained. Yeah, in 3D, Abhinav was asking before about, Anubhav was asking before about using Euler angles, for instance. That is possible. Once you accept you're going to do this nonlinear optimization. All right, so why, you might be thinking to yourself, why have we been talking so much about these convex versions of the problem if we're going to get to this in the end? I guess I admit that I am biased towards the cleaner convex formulations, partly because I think it's easier to think about them carefully. But also, there's like I have a good practical reason. And some of you heard me in Underactuated complaining about the DARPA Robotics Challenge. Okay, so we had a bunch of cool optimization-based approaches to controlling our 400-pound humanoid robot. Some of them were based on quadratic programs. That's what the balancing controller was, a quadratic program. We trusted that solver. That thing was going to run. If it ever didn't run correctly, the robot was going to fall down. That was a level of trust. We had other planning type controllers that like we're going to talk about actually next week in this class, that would figure out the path, a trajectory for the arm to move in order to do some manipulation. If the robot was standing still and we could afford the possibility that the solver doesn't return a solution, then we were actually happy to run those in the competition. But we also had like a cool class of solvers of optimization problems that could have made the robot run, walk faster, do the locomotion using nonlinear optimization. I couldn't run those in the competition. right? So I mean, flat out, you could not accept the possibility that the robot's huffing along at 400 pounds times whatever velocity I'm going, half a meter a second. It doesn't actually move that fast, but half a meter a second, right? And all of a sudden the solver says, didn't find a solution that time, and the robot goes wham. That was the reality that we faced. And as I've generally tried to get to approaches that are more robust, like more significant deployable approaches to robotics, I have favored the nonlinear solvers less. When you get to these problems, you have to accept that your perception system might actually say, not sure, okay? Now, I think for some of these harder problems, that's the best we can ask for, so I'm willing to go there. In fact, the end of the lecture is going to be like, my best recommendation to you for most of these problems is to use the nonlinear version of the problem. But I do think also, just to even understand the nonlinear versions, it's good to go through the convex versions. It helps you think clearly about what's happening. Okay, so getting rid of those constraints is one major advantage. Another sort of major advantage of switching to the non-convex problems, we can solve simultaneously for the correspondences and the pose objective. There's really no reason. I mean, the reason we didn't before is because if I C and R would be multiplied by each other. So the problem wasn't jointly convex in C and R, right? But I can now solve jointly for correspondences, let's say for C and R. But actually you could write it exactly the same way we did before, but there's actually a couple better ways to write it. Now that we're loosening up the modeling restrictions, and instead of writing there's another way to write it that actually serves us a little better here. Oops. I'm going to write it like this. Okay. The loss function here if it's a quadratic, then it's exactly what we were solving originally, but without the correspondence matrix there, right? Could have a quadratic form. That's a perfectly valid choice. But we can also do more interesting things, right? So the one we mentioned at the end of lecture last time was a truncated least squares, which looked like this, right? So this is, I'm sorry to not label my axes here. This is the distance basically between the point pairs, and this is the cost that I'm adding into my objective in these plots, okay? So one of the ways that we can be more robust to outliers is simply by truncating our cost as the distance gets higher. Okay, the CPD version used a Gaussian for this, and so it was a soft version of this. It was an upside down Gaussian because they were maximizing a Gaussian, or we flip it into minimizing the upside down Gaussian. But it's the same thing, and the important part is that it went to 0 as the distance went. It went flat as the distance went off. Okay. And there's a bunch of other versions of this that people use that are sort of the robust kernels. And a really important point to understand here is the reason these are so robust to outliers is that once you get into this flat regime, then basically every outlier over here contributes a cost, let's say it's cost of 1. And if you change the position or orientation by a small amount, right, it doesn't change how much the outlier contributes, right? There's no gradient here. The gradient is 0, okay? which means small changes in my configuration of my pose estimate, the outlier has no impact on. So so if you have an objective function, if I minimize x transpose qx, something like this, and I say plus a constant, that constant does not affect the solution at all. It's as if it didn't exist. You can just cross it out. It affects the optimum value that you'll achieve, but it doesn't affect the minimizer, okay? So that's a really important point about why these are the robust, why these, I mean, it makes sense. You set the weight effectively to 0 in the CPD case, of course that makes it go away, but equivalently in the L case here, by just setting those to a constant, that's enough. Now, the reason to switch from this CIJ version to the L version is I'm going to make one more change, and it's going to make things super fast, like really satisfying. There's a really satisfying way to avoid some of the cost of that nearest neighbor, especially the nearest neighbor from every point pair, right? So we can actually pre-compute all of our distances if we go back to this closest point idea. Which doesn't mean the non-robust thing. We can still truncate our cost with the with the flat objective here, but it means I'm only going to contribute. I'm going to only let one point effectively contribute to me, which is only the closest point. And that's really what CPD is kind of trying to do by setting all the ones that are far away to 0. Okay, so you might write that, for instance, as sum over I of L, the min over J of my x PMJ minus PSI in the coordinates. Okay, so I'm going to compute, you could think of it as computing all the distances, but only keeping the smallest one, and then passing that to my loss function. And if you're willing to think that most of the points were actually close to 0, then it's almost exact. And actually, I think it's very satisfying. Like it doesn't. Sometimes you write cost functions down and you think, yeah, I gave something up to write that cost function down. This one, it's like, no, this is what I wanted. It's good, right? So, and the reason this is so good is because it allows you to pre-compute these things by computing the distance fields a priori. Distance fields, distance functions, level sets. The one that's maybe more popular these days is the signed distance function, which is the almost the same, but the distance is considered negative if you're inside the object and positive when you're outside the object. Signed distance function. SDF, not the format, but another SDF. Okay, and these are these great things which allow you to take your model, which is not actually changing in all your optimizations, and pre-compute what's the distance from any point in space, not just where the scene points are today, but where any point in space, what is the distance from that? And then you can, when your scene points come in, you can very quickly evaluate all those scene points without figuring out who was the nearest neighbor. You can do this for models described by points. You can also do it for models described by meshes, right? It's actually sort of cleaner to think about if I had a model that was a mesh, then what am I doing when I'm pre-computing? Well, I'm saying, there's a distance of 1 that's sort of this ring here, right? There's another one that's distance 1 on the inside. Right, and there's a distance 2 out here. And you can imagine if it's really the closest distance to any point on my mesh, then I can go through and I can pre-compute that entire function, right? That's my 2-level set, 3-level set. The thing that I think is surprising that until you actually implement it or see it, you don't appreciate is that actually you can get extremely accurate representations of those surfaces with actually a pretty coarse mesh for even like the Stanford bunny. It tends to be surprising that you can approximate the value of this function. Think of this as now, even in 2D, it's just a function of x and y. In 3D, it's a scalar function of x, y, and z. So how would you represent that? You can just make a mesh in 3D, write the values of the distance at all the points. But then there's good algorithms like the fast marching cubes algorithm that try to figure out where there's a sublevel set or to interpolate nicely between them. And you can basically, even with a fairly coarse mesh, like almost like my grid points that I've got already as my background of my thing, right? If my grid points are like this and I just have values defined at the corners, it can actually still represent curves that are pretty complicated through them as trying to find a level set. Okay, with an algorithm that goes from these voxel approximations to the sublevel sets would be a fast marching cubes method, and there's a few like it.
A quick clarification question.
Of course.
So this optimization, it's speeding up that minimum computation.
Yes.
So you don't have to iterate across.
What we did before is the nearest neighbor, right? And where we actually had to like load our model points, load our scene points into this nearest neighbor data structure. This is pre-computing. So now when I go to evaluate a bunch of scene points, it's just a matter of wherever those scene points land, it's just a matter of looking up in this pre-computed function.
Got it. Thanks.
Cool. Yeah, no, it's good. Okay, now you can do this for models that are based on, if I had my models as a bunch of points too, you can get your distance functions as these sub-level sets, right? They would be defined like this and would have another one like this. Drawn badly, okay. And so you can, in the same way, you can pre-compute them. But this also maybe shows you a little bit of the quirks of having these point models. And some of the local minima we saw from the ICP was actually because it was getting kind of wedged between, almost in these little divots, right, that were happening between the points. That can be a kind of an ugly part of the solution. And oftentimes doing it on the point to plane or point to mesh is actually better in terms of getting rid of some of those local minima. So these are surprisingly good. There's, if you haven't seen, let me. Right, this is just an example from from deep SDF, which we actually will talk about later, but forget about the deep for now. This is just a signed distance function. And again, I mean, that's actually with a fairly coarse mesh in 3D. If you then go through and use these methods that try to find the zero sub-level set, that is actually the representation that people use in computer graphics to represent mesh. That is one of the representations people use to represent meshes. And to do a lot of mesh on mesh computation, this can be a really powerful tool. Okay, so let me give you one more sort of chew on this kind of slightly harder problem while I plug in I'm going to actually switch cameras so that I can plug in my laptop at the same time here. But see if you're following. I think you hit start, I hit resume. There's one more question to check yourself. So this one is borderline unfair because I haven't taught you much about optimization, but I think you don't actually need that much optimization to appreciate the solution and maybe even to have found the solution. Right, so I gave a geometric, if you clicked finish, I gave a geometric, silly, yeah, woo, I guess I didn't show my solution. You guys saw the solutions, did you? Have I been typing in solutions and nobody's seeing them? Oh man, that sucks, okay. Have people never seen the solutions I've been writing to these problems? Ah, okay, that's a fail. It's like, why would I have a field in my poll to give an explanation if it wasn't going to show it? There's a nice explanation. Okay, so let me give it now, which is that you can use the triangle inequality. So I guess the worst case, okay, I'm plugged in now, so I can go back. The worst case is when the highest cost, let's say, would be if your rotation is 180 degrees out of what you want at pi, right? So if my model points are exactly the wrong place, then, let's say I have a model point that wants to be here, and I ended up with it over here. So how much distance is that contributing to my local minima? Well, that's contributing somehow the radius of my object. So let's call that 2r. Well, if I were to rotate it at all, and the model point was over here, then how far is this, right? It's by the triangle inequality, smaller than 2r, right? And in fact, by the law of cosines, it's just it's basically what is it, square root of r squared plus r squared minus 2r squared cos theta would be the distance. So it actually goes to 0 when you're in the right place. It goes to 0 every 2 pi. Okay, and this is the bad version is the maximum, but then there's minimum in the right solution, and actually they're the only minimum. There's many minima because it's a nonlinear optimization, but they're all optimal. They're just 2 pi away from each other. Now the kind of crazy thing, if you keep going with that, I mean, I could say, okay, what if my thing was a rectangle? I didn't say anything about where the points were on the sphere, right? I could have had those 4 points that described a rectangle. I could have even had points in the middle, and then I had just another little circle on the inside that was doing the same geometry. This thing is actually good. It's a good optimization problem. I think it should always find the right solution. It's the correspondences and all the constraints you add in that make it hard. But even in the nonlinear case, this is a good optimization. It should always get you to the right solution in the known correspondences case. Even in 3D, it should do the same. I didn't actually write the distance. Yeah, sure. It's the same thing in 3D, right? I mean, you would have the geodesic on the sphere would be somehow always getting smaller. Okay. So I got one more big idea that I want to land with you today. People okay with that breakout idea? Yeah. And that is the idea of the free space constraints. And fortunately, it's actually the same idea we already did, but it's beautiful that that's true. And so let me make sure you see that, right? So first of all, what is the free space constraints, right? So if I have my object here and I have my points coming in here, if I just had a point cloud, if you just gave me a point cloud saying, fit this point cloud, then I've actually lost some information because there's extra information here about the location of the camera, right? So the the information I got from that depth image and the location of the camera was partly, yeah, of course, this is good information that there are depth values here. But maybe more important, like big idea, right, is that there's no points here. There's this whole region over there that there can't be any objects. And we're just leaving that on the table. Like we start solving these cool, convex, non-convex, whatever optimization problems, and we're kind of ignoring one of the massive pieces of information that's available. Okay, so how do you take that into account? What's actually, like I said, it's really nice. It's such a simple idea. Just add, there's actually two objects in this scene that matter in some sense. You can think of it that way. There's another object like this that is defined by the convex hull. Am I drawing that well enough? By the convex hull of my camera and the depth points. Right, so I kind of have this object, and I have this object, and they should not be in penetration, right?
Is it correct to call it a convex hull if the blue is not convex?
No, you're right. That was too sloppy. Thank you for saying that. This is just me. You're right. I'm adding a point, and that is not a convex hull. What's a better name for it? Somehow the completion of that point set or something. I don't know. Yeah, not convex hull. Thank you for saying that. But easily computed, right? So it's even though it's not the convex hull computation, you can actually just think of it as the pixels on your camera are projected into depth. I'm going to connect those with, let's say, little surfaces. Would be one approximation of it. And you might have to be a little careful around the corners, but you can also just evaluate the non-penetration at those points. But the big idea here is that think of your free space as another object that you want to not collide. Okay. I think that's I don't know if it was unique to this, but I saw that first in a paper called DART by Tanner Schmidt et al. The journal version was in 2015. Dynamic articulated rigid tracking. So I guess the version I'm doing here isn't dynamic, isn't articulated, it isn't tracking, but still I found it in that paper and I liked it a lot. So we're just doing the rigid part. I mean, the articulated part is cool that you can use some of the sign distance functions computed on each link independently as the sign distance function for let's say a multi-link robot too. Good. Does that idea make sense?
I think the paper title was real time for R, but
oh, was it real time?
Yeah.
So I'm not even doing that. Oh man, I've got nothing. Okay. Yeah, real time. It is real time. In fact, yeah, if I was more nimbly switching back between them, I would show you some videos of it. It's really good stuff. I will put a link in the notes. Okay. So actually, another thing that they did do in this paper here was they showed that you can use the SDF. One of the maybe the things that made it surprising, it was real time, but they used the sign distance function to compute the distances for the objects, for the model points, let's say models, but also for this region here. They called it the observation SDF. And we're able to show that on a GPU, you could actually make that sign distance function on the fly, at real-time rates, and do that add those non-penetration penalties to the, they did an unconstrained optimization. So they added them as penalties into the objective. Okay, so, I mean, that was our tour of geometry for finding objects in the scene. I hope it was gave you a sense. So I think maybe the summary for geometric perception, part 1. I want you to remember, think, when you hear point cloud registration, I want you to think of it as inverse kinematics. And we're actually going to go back and do more inverse kinematics on the robot, building again on some of the stuff we did here next week. But we'll do it in the context of motion planning. So I would say we talked a lot about the outliers and other things. I think the takeaway here for me today is to get all the benefits of, I think robust outlier objectives, non-penetration constraints, and free space constraints. I just think if you don't use those, you're just leaving too much on the table. Right now, today, that means you're going to be solving a nonlinear optimization. And for things, I mean, there are people that argue that you can do that just as fast as you can solve the convex optimization. Even in the year 2000, people were arguing that. Okay. But just remember that there's no guarantees. Now, people are still, this is an active area of research, trying to find better convex relaxations of the hard problems that we're talking about of non-penetration and the like. I would love if you were to check out the notes in a year for me to just change my tune on that and say, nope, we've got super solid solutions. We have the beginnings of them. We have things that can solve the problem, but just take too much time. We have things that can try to solve the problem and at least tell you if they succeeded or not. But nothing yet, I think that is quite better than what we can do with nonlinear. And we're not done with geometry, even for perception. We're going to move and do some other deep perception soon, deep data-driven perception. But the other time we're going to come back and revisit some of the concepts from geometric perception, which is why this is still geometric perception 1. Is because there's another really important class of tools from dense reconstruction. So if you wanted to build the model on the fly with your depth sensor, for instance, if you wanted to build a model of the scene, if you wanted to, there's a bunch of applications of somehow building up dense models of the geometry using your depth sensors, and those have been really fueled by some of the virtual reality, augmented reality type applications. So we'll come back to it. For instance, like the deep STF, it's also good for object representations potentially. Cool, so I actually watched the chat. I think I watched the chat this time and nobody asked any questions in chat, but it's all good. You guys have any questions?
I had one question. For trying to use the free space constraints, I've seen a variant of it where they projected the points into they basically used a depth image and used the projection to the depth image as a constraint that things have to lie behind the depth image. How does that compare to the treating it as an object version?
The treating it as an object, it might be doing the same thing. There is a slightly different formulation that I've seen that might be the one you're talking about. I think the treating it as an object, the main advantage there is the observation that you can use the sign distance functions to quickly compute all your point pairs. It's not clear to me that it fundamentally changes the geometry of your objective function.
Yeah, I'm not sure either, because the projection is at least a linear operator on your decision variables, and at least the constraint is linear then, I would think.
Careful, right? So okay, I see. So,
well, it depends on what your decision variables are. You're right. Yeah. They're not. It's not linear on the decision variables. It's linear on the projected points, or on the transformed points, which is not the decision variables.
I think it's very hard to, I mean, think of the case where you're looking at on the corner of something, right? I think those are not, the depth is not a half plane constraint or a convex constraint, right?
Right.
So I think there's hardness there either way. Anybody else? Okay. Oh, you know what? Last time I had a survey, forgot to put it up. I'm not going to make the mistake again. Don't go. Survey.
Thank you.
Sure.
Hi, I have a question.
Sure.
Sorry. So are we able to extract some local feature like edges or corners to obtain the correspondence?
That's how people used to do it. There are many variants of ICP and their derivatives where they're not doing ICP just on point pairs, but they're doing it on feature vectors, for instance. So the distance computation is based on more, normals is the, but then also RGB or edge type features, SIFT features. I think those are getting beaten now by deep features. So so you can tend to learn features and then put it potentially back in an ICP pipeline that can do better than a geometric based feature. So we'll get back to that. Yeah.
I see. Thank you.
Sure. I'm so bummed that nobody's been seeing my explanations. How can that be? Maybe you know what it is? I think it's when I don't actually have a question, like when there's not an entry. They must have seen it. You must have seen it when I had a question that you clicked submit. But maybe if I don't have any question.
Yeah, I couldn't get the answers to the first forms either.
Now that's so unsatisfying for me, especially since I moved on without saying them in the first one.
We could publish answers in the, later in PSO or something, maybe.
Oh, okay. You want to shut down the YouTube and say goodbye?